Hello everyone. Welcome to my channel Twinkle Teaches. And here is your friend Twinkle. Hope you all are doing good with your studies. As we are discussing all about topology, here is the next topic in this list. Today we will discuss a theorem on closure of a set in a topological space, which states that if x tau is a topological space and A and B are any two random subsets of the set X, such that A is a subset of X and B is also a subset of X, then we have to show that closure of A intersection B is a subset of closure of A intersection closure of B, where closure of a set A is the intersection of all closed sets containing A or intersection of all closed supersets of the set A. That is, if X is the set on which the topology tau is defined and here is a subset A of the set X, then A is contained in the closure of the set A. This is because it is the intersection of all closed sets containing A. Containment of A is important in the closure of the set A. So let us start. We will show that if any member small a belongs to the closure of A intersection B, then this member belongs to closure of A intersection closure of B. So we will reuse the result I have proved previously. I have made already a video on this topic. Closure of A is equals to A union A prime, where A prime is the derived set, which is the collection of all limit points of the set A. So let us start. If A belongs to closure of A intersection B, that is, if we say C is equals to A union B, then small a is a member from closure of C. So now, by the result, we have recently seen that closure of A is equals to A union A prime. We will expand this for closure of A intersection B. Then we can write it as A belongs to A intersection B union A intersection B prime. Now we can write it as A belongs to A intersection B union A prime intersection B prime, just because A intersection B prime is equals to A prime intersection B prime. I have proved this theorem and link is available in the description box. So by this result, we can follow the next step as A belongs to A intersection B union A prime intersection B prime. Now let us suppose this A prime intersection B prime is a set C. Then we can write this step as A belongs to A intersection B union C, where C is A prime intersection B prime. So let us come to the next step. Then it follows from the property of intersection and union that A belongs to A union C. We are opening both the brackets and again collecting them in another bracket. Then we have A belongs to A union C intersection B union C. On the next step, we will write C is equals to A prime intersection B prime. A belongs to A union, here C is A prime intersection B prime, again B union C, then B union A prime intersection B prime. A belongs to A union A prime intersection A union B prime. Here we are using the properties of union and intersection. So we can write A union A prime intersection A union B prime intersection B union A prime intersection B union B prime. Now we will again use the same result as A union A prime is the closure of set A and B union B prime is the closure of the set B. So in the next step, we can write this thing as A belongs to closure of A intersection A union B prime. We will write it as it is B union A prime intersection B union A prime and intersection B union B prime, which is nothing but the closure of the set B. Now we can use the property of intersection and we can write it as A intersection B intersection A union B prime intersection B union A prime. That is, we can change its order as everywhere we are taking the intersection of these sets. So what we get, A belongs to A closure intersection B closure intersection A union B prime intersection B union A prime from this step. Now we can write it as A belongs to A closure intersection B closure. Here we can write this because if some element is belonging to the smaller set, then that must be belonging to the bigger set. We can easily see that by the property of intersection that this is the smaller set than this set. We can tell the same thing for this portion also, that if A belonging to this set, then A belonging to this set. Similarly, we can say this for closure of A intersection closure of B. We started from the point closure of A intersection B and we reached to this member belongs to closure of A intersection closure of B. So what it implies, closure of A intersection B is a subset of closure of A intersection closure of B. Hope you all have got this theorem in which we have proved closure of A intersection B is a subset of closure of A intersection closure of B. If you have any suggestions and queries, you can ask me in the comment section or you can provide it in the email ID given here. Don't forget to give it the thumbs up if you like it. Don't forget to subscribe and press the bell icon so that you will get notified whenever I post a new video. Thanks for watching. Enjoy learning.